In this video, we're going to look at some examples of how to apply the properties from the last video. In terms of these examples, the real focus here is you're going to have to ask yourself a couple of questions. The easiest way to handle this is to simply look at it and go, where is the inverse cosine, or where is the inverse trig function occurring? In this case, it's occurring inside of this cosine function. So what I'm going to do is I'm going to rewrite this cosine function. I'm going to write it as the cosine of theta. That's going to help me focus in the concept that I'm looking for. What is the cosine of theta? I want to know what is the cosine of theta, such that my inverse trig function, cosine inverse of 0.7, is equal to theta. So this might help us revolve what we're looking at. So I'm going to start by figuring out what this theta is going to be for this situation, and then I'm going to take that theta, I'm going to plug it in here to evaluate the cosine. Now we can avoid a lot of this excess work depending on what we understand and what we know. Let's start talking about the cosine inverse function. Can the cosine inverse function pull in a value between can the cosine inverse function plug in a value of 0.7? And the answer is yes. And when it does pull that value in, the cosine function is going to take whatever angle it spits back, and it's actually going to spit out the same number, because this value right here is between the values that the cosine inverse can take in and then immediately spit back out if it's undoing itself. So again, in this case, the cosine and cosine inverse will cancel each other out and I'll be left with 0.7. If you're not comfortable with that, maybe you struggle with the concept that 0.7 isn't a value on the unit circle, so we have difficulty following through with that. Well, we can go ahead and use our calculator here to go ahead and start by identifying cosine inverse of 0.7. So I'm going to go ahead and do that. Alpha cosine of 0.7. I'm going to close the parentheses. I'm going to hit enter. That's going to be approximately 45.5729 degrees. This value here isn't on the unit circle. Now it is a value in the 360 degrees that we're referring to in the unit circle, but it's not quite 45 degrees, so it's not really pi over 4. So if I take that number and I take the cosine of it, so I'm going to go ahead and do that. Let me go ahead and second cosine of the previous value here, do my best of the ability to include all the possible numbers there, and I'm going to go ahead and hit enter on that. It's going to give me back the exact same number, 0.7. This is completely valid because cosine of cosine inverse of a number is equal to that number if and only if it's between 1 and -1. So if there was a 2 here, this would be undefined. It would not have a solution. If it was any other number between 1 and -1, then this is perfectly fine. So let's take a look at another example. This one might be a little bit more in our wheelhouse. How about the sine inverse of sine of pi? So for this one, again, if the sine function is there, we can just straight look to the unit circle and start asking ourselves some questions. In this case, we're looking at the sine of pi. The sine of pi sits over here. Well, the sine of pi there is going to be -1 comma 0. So I know that that right there is going to be the same thing as the sine inverse of 0, because I know that the sine of pi is actually a value of 0. So then the question comes down to, well, where is sine inverse of 0 going to be? What value am I going to get back for this? Well, if we recall, sine inverse can only spit values back between here and here, and the only location where the y value is 0 is right here. So that means that it's going to be an angle measure of 0. You can use 0 degrees or 0 radians. Either one's going to be fine, but notice how the rule from the previous video supports the range of values that we were allowed to utilize this for. Because it's sine inverse of sine of pi, and the value that's in here is not somewhere between pi over 2 and -pi over 2, it didn't spit back the same number. But now I can still evaluate that pi and get back a number. That number just has to be in that set of values there. Another example we might look at is, say, the cosine of cosine inverse of -1.2. You should immediately have bells ringing in your head saying, nope, 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 because the cosine inverse and the sine inverse function both can't take in any values if they're larger than 1 or smaller than -1. So this is straight up undefined. There is no value that this function will spit back. And again, cosine of cosine inverse is perfectly fine, but the minute I plug a number in here that doesn't make any mathematical sense, the function breaks. Another example we might look for, and this is where we're going to go ahead and talk about this. This is an exact value setup. This right here is an exact value setup, but this we might be able to use a calculator for simply because we don't know what those values are. This next one, it will specifically say find me an exact value. And the reason why it will do that is because it doesn't actually comfortably use the setup of the previous properties. So I'm going to have sine of tangent inverse of 3/4. Let's take a second for a minute to talk about what this is going to be. Now, I tried to start setting up the concept of what we're going to work with here in the first example. I said, well, if I've got an inverse trig function on the inside, let's call that theta, and then let's bring that out. I'm going to do the same thing with this one. Again, I don't have sine of sine inverse, so this can't just simply cancel each other out and give me back 3/4. So I'm going to go ahead and say I'm looking, every inverse trig function is equal to an angle. I'm going to call that angle theta. In that case, I know tangent inverse of 3/4 has to be equal to theta. And I'm looking for the sine of theta. Well, let me go ahead and take a second here. Let me manipulate this, and I'm going to have tangent then of theta equals to 3/4. And I'm going to stop and I'm going to ring a bell here, and I'm going to say, wait a second. Every tangent of theta, every trig function, not inverse, every basic trig function is supposed to be equal to a ratio of values from a triangle. Well, if this isn't on the unit circle, if this isn't a value that I know quite easily on the unit circle, which again is not, I know radical 3, I know radical 3 over 3, I know 1, and I know some undefined and 0 values. But nowhere on the unit circle does tangent of theta ever equal to 3 over 4. If that's the case, your first instinct is to take this thing right here and it's to build a triangle. Because again, that's where all trig functions initially came from. So every once in a while, we're going to have to go back to that basic form to work through it. Again, if it didn't say exact, we'd be able to use a calculator. But because it says exact, we have to do it this way. So tangent of theta is supposed to be equal to 3 over 4. So sine over, the opposite over adjacent. And then I'm looking for sine of theta, so I'm looking for the opposite, 3 over the hypotenuse. Well, I better go ahead and find that hypotenuse. Remember, 3 squared plus 4 squared is equal to the hypotenuse squared again. Leg 1 squared plus leg 2 squared is equal to the hypotenuse squared. In this case, that value is actually just going to be 5. So my sine of theta is simply based on this triangle, 3 over 5. That's all we have to do. That's it. Again, it seems like there's a lot more work that's going on here, but don't be afraid that every inverse trig function is equal to an angle. Force it to happen, plug in the sine of theta, and then you're knowing that I can build a triangle from this one, and then I can solve sine of theta from that triangle. The last example we're going to work with in this case is going to be very similar to that example right there, where we look at another cosecant in this case. A cosecant of sine inverse of a negative 1/2. The reason why we're going to have to talk about cosecant is because, well, we didn't talk about any of those cosecant, secant, or cotangent functions. Well, the reason why we didn't talk about them is because we don't necessarily have to. We can work with their basic standardized functions. We can change this cosecant function to be 1 over what it is, sine, and then we can work from there. Just like that of if we had a cosecant inverse function here, we can work with that first and then go back to where we need to be. So for this one right here, we're going to go ahead and do the same thing we did in the last example, and that's go ahead and force the inverse trig function to be equal to an angle. We're going to call that angle theta. So sine inverse of a negative 1/2 is equal to theta. That means that somewhere on the unit circle, or I can build a triangle out of sine of theta equaling to a negative 1/2. Well, in this case, negative 1/2 is a unit circle value. So maybe I should be working with a unit circle here, and that does make the most sense. Especially with negative numbers, it's going to be kind of difficult to build a triangle out of this, although if I wanted to build a triangle of this, I could. I could quite easily build a triangle such that I have theta, a right triangle, and then sine is supposed to be negative 1 over 2. Well, it's opposite, 1 over hypotenuse 2, and the radius in the unit circle, and therefore in almost every other triangle, will always be positive. So I'm going to call that a negative 1 value. Again, if you wanted to see this appropriately using the unit circle, well, I'm going to build a triangle somewhere in one of these two quadrants, and since sine is negative, we're going to be down here in this quadrant. So really this triangle is actually going to look more like this in that triangle, or in that unit circle, where this is your negative 1 and this is your 2. So you don't necessarily have to go back to the unit circle. You could simply go ahead and build a triangle in every single one of these examples, as long as it's evaluatable there. Well, in this case, I can go ahead and solve for this missing side. That missing side, if I do it correctly, is negative 1 squared plus a missing side, b squared, is equal to 2 squared. This is going to be 1, this is going to be 4. I'll subtract the 1, and I'll end up with, well, square root of 3. You'll notice over here then that that's going to be a radical 3, and I can go ahead and evaluate what is the cosecant of theta. Well, the cosecant of theta is the same thing as 1 over the sine of theta. Well, the sine of theta was simply this over this, so I'm just going to get back, well, a negative 2. So that's how we can build these triangles in such a way that we can evaluate them in a very specific way. It's a matter of taking the time and the effort to build the triangle or go to the unit circle. And again, if you use the unit circle, the same thing would happen. We would simply come around with the x and y coordinates, and then we would say, well, I want cosecant of that. Well, the cosecant is the reciprocal of sine, so I would just flip that sine value. You could do some manipulations here, some smooth manipulations here, but I would strongly recommend you avoid doing that. One thing you could view this as, and this is the only thing I think you could do, is say that this is the cosecant of something. The cosecant of anything is 1 over the sine of that anything, therefore giving you the sine inverse of that 1/2. This is mathematically the same thing. Then, because it's sine inverse of, negative 1/2, it's sine inverse of negative 1/2, that's a value between negative 1 and 1, and therefore the sine and sine inverse can cancel each other out, and I'll still be left with that negative 2 value. That might be something that we can do, but this is a better way to do it for all general examples when working with them.